where these filaments intersect, galaxies stick closer together, forming a cluster. The theory goes that if there were no dark matter, galaxies would be distributed evenly throughout the universe, which obviously isn't the case. While many galaxies in the Perseus cluster are already known, cosmological simulations predict there should be several dwarf galaxies there too. If we could see those faint galaxies, we could analyze their shape and distortion relative to the cluster and background to determine how dark matter is distributed. The problem is, these dwarf galaxies tend to be overshadowed by older stars shining infrared light, so they've evaded direct observation. Until now. Euclid discovered more than 630 previously unknown dwarf galaxies, which is a huge breakthrough in the study of dark matter. More than dark matter, Euclid is also teaching us about star formation too. Let's go to our next destination and I'll show you. Say hello to irregular galaxy NGC 6822, shining bright 1.6 million light-years away. It was first identified as a remote stellar system by Edwin Hubble in 1925. Now, almost 100 years later, Euclid is sending back high-resolution images of the entire galaxy and its surroundings. The James Webb Space Telescope did also image this galaxy a few years ago, but a much narrower field of view. Scientists are interested in Euclid's wide-angle photos of this galaxy for what they might tell us about star formation and the early universe. You see, stars smash lighter atoms like hydrogen and helium together to produce heavier atoms, including metals. This process happens across a star's lifespan, and is why we don't see many heavier elements in the early universe, because they take time to accumulate. Surprisingly, many of the stars in NGC 6822 have very low levels of metal atoms. By studying low metallicity galaxies like this one, scientists hope to learn more about how galaxies evolved in the early universe. Euclid has made that a monumentally easier task thanks to the color information from its NISP instrument and its wide field of view. Euclid has also revealed several previously unknown globular star clusters and H2 regions in this galaxy. H2 regions are the colorful gas clouds we see here. When stars are born, they emit light so strong and bright that it ionizes the hydrogen gas surrounding them, resulting in these H2 regions. Studying these will help us better understand the cloud properties at the time a star is born, and what conditions are needed for massive star formation. Speaking of globular clusters, here's one in a different part of the sky. Globular cluster NGC 6397 is 7,800 light-years from home, making it the second closest one to us. This image is one part of a wider image from Euclid, which I'll show you in a little bit. Globular clusters are kind of like Hollywood, a high concentration of stars in one place, where everyone is trying to outshine everyone else. What does this mean? The smaller, dimmer stars get drowned out by the bigger, brighter ones. On top of that, they extend quite a long way out from their center, with the radial parts mainly made up of low-mass, faint stars that, until now, have been hard to see. Ironically, it is these faint stars that hold the most scientific interest for unlocking the history of the Milky Way. As David Massadri of the National Institute for Astrophysics in Italy puts it, currently no other telescope than Euclid can observe the entire globular cluster and at the same time distinguish its faint stellar members in the outer regions from other cosmic sources. Hubble actually imaged the center of this cluster in 2021, but to image the entire cluster, including the sprawling outskirts like Euclid did, would have taken it far too much time and resources. On the other hand, Euclid snapped this shot in just 1 hour, and it is absolutely beautiful, both aesthetically and scientifically. Sometimes we see stars arranged like this, and sometimes we see them arranged as spiral galaxies. Yet, despite living in one, we don't actually know how they maintain their shape. The next Euclid pictures aim to help answer those questions. It's worth noting that the technology that allowed Euclid to capture these images wasn't cheap. ESA spent an incredible 1.4 billion euros on the development, construction, launch, and operation of Euclid. Anything that might have reduced that cost to get that data about our universe would have surely been welcome. Well, we might not be able to help with that, but if you're trying to see the sights around Earth and are struggling to keep the costs of buying data down, the sponsor of today's video, Eralo, can help, and are even offering a special $3 discount off their price if you use my code ASTROM3. Having data and SIM coverage when you're abroad is a must, as any frequent traveler will tell you, but roaming can be expensive. Eralo is an eSIM marketplace that lets you select an eSIM from over 200 different countries or regions at prices as much as 10 times cheaper than you'd otherwise be paying. I found it super easy to set up in just a few minutes, and if you're still worried, you can reach out for help from their support team 24/7 for whatever little hiccups life might throw at you. If you want the peace of mind of knowing you've got data coverage sorted wherever you travel in the world for a low price, why not follow my link eralo.com/astromspace or scan my QR code to download the app. If you use my code ASTROM3 at checkout, you'll receive $3 off your first eSIM. Give it a try. Caldwell 5, also known as the Hidden Galaxy, is hard to observe because it lies in the busy disk of our Milky Way, about 11 million light years away. It tends to get overshadowed by dust, gas, and other stars. It is considered a look-alike galaxy to our own, which makes it a prime point of interest for researchers. It's pretty hard to study a galaxy you're inside of, since you only get to observe it from one plane. Euclid's near-infrared instrument was able to pierce through the dust and reveal the galaxy in all its glory. We've captured it before from the ground, but with nowhere near the detail Euclid manages. The Euclid image might look normal, as if every telescope can make such an image, but that is not true. What's so special here is that we have a wide view covering the entire galaxy, but we can also zoom in to distinguish individual stars and star clusters. We can trace the history of star formation and better understand how stars formed and evolved over the lifetime of the galaxy, says Euclid Consortium scientist Leslie Hunt. We still don't fully understand how spiral galaxies maintain their structure, or the role dark matter plays in forming them. Euclid's ability to capture this galaxy's sprawling spiral arms and dust lanes in such detail will help scientists understand the link between dust, gas, and star formation on a large scale in a way we've never been able to before. Sadly, we've only got one more stop on this cosmic tour, but I've saved you the best for last. Let's see what these colourful clouds are hiding. Our fifth and final photo shows the Horsehead Nebula. It has been photographed by various telescopes before, but never with such a sharp and wide view as Euclid managed. Again, this shot was taken in just 1 hour, which is absolutely mind-blowing. It's like someone just stopped at a viewpoint and snapped a picture. Located approximately 1,375 light years away, this is the nearest massive star-forming region. It lies just south of Alnitak, the easternmost star in Orion's 3-star belt, and is part of the expansive Orion Molecular Cloud. It is in this swirling nebula that scientists hope to find evidence of many previously unknown Jupiter mass planets. One such planet has already been identified, Sori 62, a young planet 10 times the mass of Jupiter and a temperature of 1,200 degrees Celsius. The clouds behind the Horsehead Nebula are illuminated by UV radiation from nearby star Sigma Orionis, while the clouds of the Horsehead Nebula itself are made up of cold molecular hydrogen, which gives off barely any heat or light. This makes the Horsehead Nebula an interesting place to learn more about star formation, as scientists can observe and compare how stars form in dark versus bright clouds. Sigma Orionis is part of a group of stars called an open cluster, which researchers hope to get a more complete picture of with Euclid's data. For example, free-floating planets have been known to exist in Sigma Orionis, but with Euclid's ultra-high sensitivity, scientists found many smaller FFPs than were previously documented. As one research paper put it, FFPs in that zone appeared to be ubiquitous and numerous. And this is just the beginning. With another 5.5 years of mission time left, Euclid still has a lot of ground to cover. Along the way, the data and images it collects will be pivotal to helping scientists unravel the mysteries of dark matter, dark energy, and the origins of stars, galaxies, and the universe itself. A 3D map of the distribution of dark matter could be revolutionary to our understanding of fundamental physics. Until then, we'll just have to entertain ourselves with more images as they come out. Thanks for watching. If you like this video, you may like my other videos on space tech and innovation. Did you hear about JAXA's precision landing on the moon? It has the potential to catapult us into a new era of planetary exploration, but it didn't totally go according to plan. Click here to watch it now, and I will see you next time.